Hello, welcome to my presentation video on the effects of harmonics in neutral conductors. My name is Martin Lavachka, and in this video I'm going to talk about the generation of harmonics in the neutral conductor, its effects on the electrical installation, and solutions to manage harmonics in the neutral conductor. Third harmonic currents are specifically responsible for increasing neutral currents in three-phase four-wire systems. In a three-phase system, third harmonics are generated only by nonlinear single-phase loads supplied between phase and neutral. When multiple nonlinear single-phase loads are supplied, the third harmonics of each phase accumulate in the neutral, which can cause an overload of the neutral conductor. This is not a general situation because power is being supplied simultaneously to linear or three-phase loads which do not generate third harmonic currents. In the image, you can see the nonlinear phase currents and the resulting nonlinear neutral current in a three-phase four-wire system supplying identical single-phase loads. In this example, the RMS value of the neutral current is equal to square root 3 times the RMS value of the line current. However, when the loads include partially linear circuits, such as motors or heating devices, the RMS value of the neutral current is strictly less than square root 3 times the RMS value of the phase currents. On the right, we can see the harmonic spectra of the phase and neutral currents. It can be seen that the neutral current only includes third or triple harmonics. The amplitude of these currents is equal to 3 times the amplitude of the phase currents. In neutral current measurements, the third harmonic has the largest magnitude and the other triples decrease significantly in magnitude, so they do not contribute significantly to the RMS value. Harmonics are generated by the nonlinear loads of the installation, such as computers, fluorescent lighting, LED lighting, rectifiers, and electronic power choppers. Office buildings and computer centers are often subject to the circulation of high levels of triple harmonics, particularly third harmonic current. The third harmonic ratio has an impact on the current in the neutral and therefore on the capacity of all the components of an installation, such as distribution panels, protection and distribution devices, and cables and trunking systems. Therefore, it is important to select the optimal size of neutral conductors in installation where neutral conductor overload is a major concern. In the image, you can see different line current waveforms for different amounts of nonlinear load with the active power maintained for linear loads. In this graph, you can see the different relationships between neutral currents and line currents. As the number of single-phase nonlinear electronic loads connected to the same neutral increases, the third harmonic ratio also increases. According to the estimated ratio of the third harmonic, there are three possible scenarios. Ratios less than 15%, between 15 and 33%, or greater than 33%. If the third harmonic ratio is less than 15%, then the neutral conductor is considered unloaded and the size of the phase conductors only depends on the phase currents. According to the IEC standards, the size of the neutral conductor can be smaller than that of the phase conductors if the CSA is greater than 60 mm² for copper conductors or 25 mm² for aluminum conductors. If the third harmonic ratio is between 15 and 33%, then the neutral conductor is considered to be carrying current and the practical current should be reduced by a factor of 0.84. The size of the neutral conductor must be the same as that of the phases. This generally leads to the selection of a busbar trunking system whose current rating is immediately greater than the requested capacity. If the third harmonic ratio is greater than 33%, the neutral conductor is considered to be carrying current. The current in the neutral is equal to or greater than the current in the phases. Neutral current predominates in the selection of conductor size. The recommended approach is to adapt circuit conductors of the same size for phase and neutral. This generally leads to the selection of a busbar trunking system whose current rating is greater than the requested capacity, generally by a factor of 2. As an example of how the reduction factor due to harmonic works, let's consider a three-phase circuit with a design load of 37 amps that will installed using a 4-core PVC insulated cable clipped to a wall. A 6 mm cable with copper conductors with a current capacity of 40 amps is used, suitable if there are no harmonics in the circuit. But if the ratio of third harmonics is 20%, then a reduction factor of 0.86 is applied and the design load becomes 43 amps. For this load, a 10 mm cable is necessary. If the ratio of third harmonics is 40%, then the cable size selection is based on the neutral current, which is 44.4 amps, and a reduction factor of 0.86 is applied, leading to a design load of 51.6 amps. For this load, a 10 mm cable is suitable. If the ratio of third harmonics is 50%, then the cable size is again selected based on the neutral current, which is 55.5 amps. In this case, the ratio factor is 1 and a 60 mm cable is required. The graph on this slide represents the maximum admissible phase and neutral currents per unit in a high-power busbar trunking as a function of the third harmonic level. Since additional power losses occur, a reduction factor for the phase conductors is necessary. This was already explained in the previous 4 slides. The reduction factors also take into account the heating effect of harmonic current in the phase conductors. The circulation of harmonic currents produces additional heating within the conductors for several reasons. The heat is produced as a result of the additional high levels of triple harmonic currents, compared to the relatively minimal current flowing in the neutral for normal balanced linear loads, and additional heating of all conductors due to increased skin effect and eddy current losses due to the circulation of all harmonic orders. We are going to compare the results of heat measurements performed on two different types of busbar construction, both with the same CSA total of active conductors, 200% neutral and 100% neutral standard. On this slide, we can see the comparison between two busway constructions with the same test conditions for both cases. The phase current was 1600 amps, the third harmonic ratio was 33%, and the neutral current was 1520 amps. The result was that a busbar trunking system with four identical conductors would have a lower temperature rise than a 200% busbar with the same CSA total. In conclusion, the most effective solution is to reduce the current density in all conductors by selecting the appropriate busway rating with a single neutral. If the neutral conductor is sized correctly, including harmonics, overall protection of the neutral conductor is not required because it is protected by phase protection. However, in practice, if the CSA of the neutral conductor is lower than the CSA phase, neutral overall protection must be installed. Now, if the CSA of the neutral conductor is equal to or greater than the CSA of the phase conductor, no specific short circuit protection of the neutral conductor is required because it is protected by the phase protection. If the CSA of the neutral conductor is less than CSA of the phase conductor, then neutral conductor must be protected against short circuits. In high power installations, various factors contribute to reducing the ratio of third harmonics in neutral conductors, such as more and more high quality IT equipment, including power factor correction circuits, HVAC equipment in large buildings that are supplied by a three-phase network and as such do not produce triple harmonic currents, or fluorescent lighting equipment that generates triple harmonic currents which are phase shifted with harmonic currents generated by PCs, giving a partial vector cancellation. We come to the end of this presentation. Now you know everything about the effect of harmonics on neutral conductors. Thanks for watching.